We're at the point in the course where we start looking at different rules for finding derivatives of functions, different shortcuts. The only one we've really looked at, or the main one we've looked at, is the power rule, which tells you that if you want the derivative of x to the power of n, that it's n times x to the power of n minus 1. Applying a few other basic rules like, the derivative of a constant is 0, which is really actually a special case of the power rule, and the rule for summing the sum of two derivatives and the constant multiplier rule. We're able to do some derivatives, mostly polynomial functions and a few others. Now I've got an example here where we're talking about y equals x squared plus 3x times x squared minus 7. You might guess at the derivative of this function and say, well, I know that x squared plus 3x has a derivative of 2x plus 3, which is a correct statement to make. And I also know that x squared minus 7 has a derivative of 2x. So I'm going to go out and I'm going to say that the derivative of this function must be 2x plus 3 times 2x, the derivative of the first set of brackets times the derivative of the second. And as it turns out, that is incorrect. Okay, so the answer to that question is a definite no. Why do we know that that is incorrect? Well, we know that if you were to take this and simplify it, okay, you would get a degree 4. A degree 4 function simplified. If you take the derivative of a degree 4 function, you're going to get a cubic or a degree 3 function. And the first term, in fact, will be 4x to the power of 3. Well, look at what we got here. I mean, this is 4x squared plus 6x. That's not going to be the derivative of this. So it's incorrect. You can't just multiply derivatives together. The derivative of one function times the derivative of another function, okay, doesn't work. We need what's called the product rule. So to start with today, we're going to work on the product rule, and it's going to tell us how we can take the derivative when we have two things multiplied together. And at first, it won't allow us to do a whole lot of new stuff, but it will allow us to take derivatives of stuff like this without needing to multiply it together. So let's take a look. So here it is. Here's the product rule. The product rule tells us that if f of x is equal to p of x times q of x, then the derivative of f of x is actually p prime of x times q of x plus p of x times q prime of x. So that basically means that if you have two factors in a product, that the derivative is the derivative of the first factor times the second factor plus the first factor times the derivative of the second. Meaning that if I actually wanted to do this question up here, the correct way to do it would be to say dy by dx is equal to the derivative of the first, 2x plus 3, times the second, x squared minus 7, plus the first, x squared plus 3x, times the derivative of the second, which is 2x. Unsimplified, but there is actually the correct derivative of this right here. If you don't believe me, well, you could expand this, okay? And you could expand this and take the derivative, and you find that you do, in fact, get the same thing. And by the way, this is, of course, a cubic function. You have a 2x cubed and another 2x cubed. There gives you that 4x cubed that we know we should see in the derivative. Now, this is the product rule in prime notation. In Leibniz notation, it's not we don't use function notation, so we actually could just say the derivative of uv. And here u and v are constants. They're functions. Okay. The derivative of uv with respect to x is the derivative of u with respect to x, which is du by dx, times whatever v is, plus u times whatever the derivative of v is. So in Leibniz notation, it's kind of slick. Okay, because you don't need to say let y equal uv. You can just say the derivative of uv with respect to x is the derivative of u with respect to x times v plus u times the derivative of v with respect to x. We will quickly outline the proof of the product rule. So if f of x, let f of x equal p of x times q of x, and then our goal, if we use this, is to show that this is true right here. Okay, it's not obvious how to do this proof, but none of the steps are super complicated. Okay, we have to do first principles here because we're trying to prove a derivative shortcut, so we go back to first principles. Now in this case, since f of x is p of x times q of x, f of x plus h is now p of x plus h times q of x plus h, and f of x is p of x times q of x. Notice, of course, that this limit is indeterminate. If you sub in h equals 0, you get p of x q of x minus p of x q of x, which is 0 over 0. Okay, the key to this proof, and this is kind of like if you ever wanted to reproduce this proof, like when I wanted to come up with this proof to show you guys, I had to know this little fact that I have in fact put in red for you. I'm going to take this right here and I'm going to add p of x times q of x plus h and subtract that. So that's allowed because I'm really adding 0. Okay. Why that? Because that's what makes it work out. So that's, again, that's just kind of one of those, to do this proof, I kind of had to know that that's how it's done. And this certainly allowed. Now, all I'm doing here is taking that amount that I've added and subtracted, and I have chosen to write it in the middle. So I'm just, there's 1, 2, 3, 4 terms I'm adding and subtracting, so I can scramble them up into whatever order I want. I'm going to go with the subtraction first and then the addition. And the reason I've done that is actually now, if you look at the first two terms, they actually have a common factor of q of x plus h. So there it is right there and right there. So that's a common factor. Okay, I'm going to factor that out. And then the second two also have a common factor. In this case, the common factor is p of x. So on the next line, I'm going to factor the first two, and I'm going to factor the second two, and we'll see what we get. Okay, and there you have it. So like I said, q of x plus h is a common factor for the first two, which leaves you with p of x plus h minus p of x. Then p of x is a common factor for the next two, which leaves you with those right there. Now what I'm going to do is I'm actually going to break the limit up. So I am allowed to take the limit and add two limits together like that. Okay, so I've basically taken this half and split them up into their own limits. From that, I'm actually going to take the, I'll show what I'm going to do here. I'm now going to take this and express it as a product. So it's the limit of this times the limit of that, and the limit of this times the limit of that. So first I took this fraction, I broke it up into addition. Then I took it and I broke it up into multiplication. Now we didn't do a lot of properties and limits, but these are both allowed. From there, look what I've got. The limit is h approaches 0 of q of x plus h. Well, just sub in h equals 0 and you just get q of x right there. Next, I'll skip over here. The limit is h approaches 0 of p of x. Well, that's just p of x. And then now look at this little line right here. This is the definition of the derivative if you were using p of x instead of h of x. Sorry. This is the definition of the derivative if you were using p of x instead of f of x. So really, that's just p prime of x. And the same thing works over here. This is the definition of the derivative for q of x if you're using q of x instead of f of x. And so we get right there, and then we are done. It has been proven. Next, let's look at a simple example of just using the product rule again. So I've got this messy, it's a polynomial. I could expand it and find the derivative that way, but often it's easier just to leave it alone and use the product rule, and we're demonstrating the product rule. I'm going to use some lazy notation instead of dy by dx. Actually, I was going to say I was going to use y prime, but I'm going to go with that. So it's the derivative of the first, which is 2x plus 3, times the derivative, or sorry, times the second, with not taking the derivative. Okay, plus the first, x squared plus 3x minus 4, times the derivative of the second, which is 3x squared minus 4x minus 1. Now we were asked to figure out what dy by dx was when x is equal to 1. I like this little notation here. Rather than saying when x equals 1, the bar with the x equals 1. I've seen that a few times before. Well, 2x plus 3 is just going to be 5. And here we're going to have 1 minus 2 minus 1 plus 7, whatever that is. Here we're going to have 1 plus 3 minus 4. And here we're going to have 3 take away 4, take away 1. And this part of the problem is kind of boring. 5 times 1 minus 2 is negative 1, negative 2, 5 again. Plus, let's see, 1 plus 0. So 25 is the answer there. And there you have it, the slope of the tangent, or the derivative of y is 25 at x equals 1. So the product rule is not super difficult to use, and that brings us to the second part of the lesson where we sort of introduce a new rule as well. So we're going to take the derivative of this equation using the product rule, not by expanding. So f of x is, of course, 3x plus 1 times 3x plus 1. So to take the derivative of this using the product rule, f prime of x is equal to the derivative of the first, which is 3, times the second, which is 3x plus 1, plus the first, 3x plus 1, times the derivative of the second, which is 3. Now, I'd like you to notice that we have the same term, and that's not super surprising, okay? Since they're both 3x plus 1, the first step, taking the derivative of that times that, and the second step, the derivative of this times this, give you the exact same thing. So I know this is a bit strange to write this, but I could really say that I have 2 times 3x plus 1 times 3. Why am I doing that? Because I'm basically saying, look, I have this term right here. I have this term. I have it twice. So just times it by 2. And there you go. Yeah, the 3's here, but it could be there. Okay, I'm doing this to show you a pattern. I know you're wondering right now, why wouldn't you make that 6? Well, I would in the next line, of course. Okay, let's look at what happens with the power of 3. So in order to discover a new rule, let's look for a pattern in doing some of these derivatives. This is f of x equals 3x plus 1 squared, which of course means that f of x is just 3x plus 1 times 3x plus 1. Using the product rule, I can say that f prime of x is the derivative of 3x plus 1, which is 3, times the second, plus 3x plus 1, times the derivative of this, which is 3. Now, I'd like you to notice that these terms are the same, okay? Now, adding two things that are the same, 3x plus 1 times 3, okay? I have this twice. So really, I could say that I just have this. I know that that's a bit odd. I mean, you might be immediately saying, well, why don't you just say you have 6 of them, which is true, I do, but I'm looking for a pattern. So that's what I actually want to write, okay, for now. Okay, I've got 2 of the same thing. Anytime you have 2 of the same thing, you could just multiply by 2. Let's continue this idea, and let's look at something to the power of 3. So now what I have is I have 5x squared plus 1 times 5x squared plus 1 times 5x squared plus 1, like so. We haven't done this yet, but if I want to apply the product rule to 3 terms, I can do that. I'm basically saying, hey, look, this is a product. Here's the first term times the second term. So you do the derivative of the first, which is 10x. You times it by the second, which is all this stuff here, all this stuff right here. Five x squared plus 1 times 5x squared plus 1. And then you do the first times the derivative of the second. Okay, so you've done the first derivative times the second, which is all this stuff. Well, now we do the first, 5x squared plus 1. And we times that by the derivative of the second. Well, if the second is all this stuff, then we have to apply the product rule again. So what ends up happening is you just end up doing the product rule another time. So basically you have 3 terms, and each time you take turns with which factor gets to take the derivative. So 5x squared plus 1 times 10x times 5x squared plus 1. Sorry, no, let's do it. 5x squared plus 1. There we go. Okay? Now, the third one does the same thing. Just like that. I kind of always think of it, I know this is a little bit silly, but I always think of it as each of these factors gets a turn at being the derivative. I get to be the derivative first, 10x, times the other 2. Now I get to be the derivative times the other 2. Now I get to be the derivative times the other 2. Now, in this special case, because all these factors were the same, there's some patterns that emerge. First of all, 5x squared plus 1 times 5x squared plus 1 is actually 5x squared plus 1 squared. So there's a common term that appears every time, and instead of being 2 of them in this case, there's 3 of them. 3 5x squared plus 1 times 5x squared plus 1 times 10x. We have the exact same term every time. I've just chosen the 10x is just appearing in different spots, but that doesn't matter. Or better yet, I could say f prime of x is 3 times 5x squared plus 1 squared times 10x. And yes, you can simplify this further and say that that's 30x, but I'm leaving it like this because I want you to see the pattern that's going to arrive. Imagine I were to take 5x squared plus 1 and do it to the power of 4. What would I get? You can kind of see now. You would end up doing the product rule. You'd have 4 terms in the product rule. Each one will get a turn at being the derivative is how I like to think about it. So you've got this 4 times now. And if you imagine just even doing the first part of it, okay, you would see that the first part would end up being, you would have 3 of these multiplied together, 5x squared plus 1 cubed, and then one of them is the derivative, 10x, just like in the example up above here, okay? But now you got 4 of those instead of 3, okay? And each time, so just imagine again doing the first one, you know, this would be 10x times that, times that, times that, which gives you this right here, but you get the same thing every time, so there's 4 of them. And there's a pattern that we can see now in all of these answers if we just look closely. Let's take a look at the first. So let's just think again, about when you have, you know, y equals x to the power of 4, then y prime, or dy by dx, is 4x cubed. That's the power rule. That pattern is actually showing up in the work that we're doing right now. Here we had f of x equals 3x plus 1 squared. And look what we get down here. 2, it's like we brought the 2 down, made that a 1. And then, of course, we got this 3 here. We'll worry about that in a second. And in the second one, that similar pattern is there. We get 3. So here is the final answer down here. We get the 3 comes down here, okay, just like in this example with a 4, though. Okay, and then the exponent drops to 2, and then we end up with this 10x here. And in the last one, the same thing happens. The 4 comes down here. Okay, the exponent drops by 1 to a 3, but then we have this 10x. So really, this is a lot like the power rule. The only difference is we treat this like it's a power. We do 2 times 3x plus 1 to the power of 1, but then we multiply by the derivative of what's on the inside. Same here. Bring the 3 down, okay, 5x squared plus 1 squared, and then multiply by the derivative of the inside, which is 10x. Same thing here. Bring the 4 down, okay, the exponent becomes a 3, and then we multiply by the derivative of 5x squared plus 1, which is 10x. So could you see that without using the rule yet, or me giving you the official rule, let me just make one up. Imagine I had 3x cubed, let's make it a little harder, to the power of 9. Okay, you certainly don't want to do that by multiplying it out 9 times. Can you see what we would do here? We would say f prime of x, bring the 9 down, just like we're doing the power rule. The only difference is we then take, sometimes people say multiply by the derivative of the guts or the base of the power, which in this case is of course that, 3x cubed minus x, which has a derivative of 9x squared minus 1. So there is that derivative all in one step. And now we're ready to sort of formally introduce what I call, and I think your textbook calls it this as well, the power of a function rule. So it's basically saying, look, if you have a power, but instead of let's go back to our regular power rule. If f of x is equal to x to the power of n, then f prime of x is equal to n times x to the power of n minus 1. Basically, this is now modifying and say, okay, imagine x isn't just x. Imagine now it's some other function. Well, the derivative is n times the other function to the power of n minus 1 times the derivative of that inside function. That's exactly what that's saying. Or, in Leibniz notation, it's a little bit slicker, I think, to be honest. The derivative of u to the power of n is equal to n times u to the power of n minus 1 times the derivative of u with respect to x. So to take the derivative of a power, do n times u to the power of n minus 1, and then multiply by the derivative of the base. Now that actually is, you could actually say that the power rule covered before is just a special case of the rule above. Because if I wanted to use this rule with a regular power, I might say, oh, y equals x cubed, so y prime is 3x squared, but don't forget to multiply by the derivative of x. Well, the derivative of x is just 1, so we don't need to worry about it. Not only that, I will point something else out, and I should say this now. If you were to talk to a student in university who has a good understanding of calculus, or even think about yourself in about 2 weeks' time, okay, you would never see this as the power of a function rule. So if you told, your friend who's in university calculus, today I learned about the product rule, and they say, oh yeah, that's good, and you could mention some other rules, and they'd be like, oh yeah, I know that. But if you said power of a function rule, they might be like, oh, I don't know what that is. Because really this is something bigger called the chain rule. You're just not really ready to see the chain rule yet. But if you were to look back at this note of this video while you're studying, you're learning the chain rule. Anyone in a first year university or has finished this course would look at this and say, that's not the power of a function rule, it's called the chain rule. But for now, it's good to think of it as the power of a function rule, and we'll continue to call it that for a little bit. So this is almost for worry about this later. What's the chain rule? You don't know. You'll learn it later on. But if you were to look back, you might want to have that note there. So a simple example of using the power of a function rule, here we could say dy by dx is equal to 4 times x cubed plus 2x squared minus 1 to the power of 3. That's kind of your power rule, but multiply by the derivative of the base, which is, of course, 3x squared plus 4x. And there it is. Now, do you need to expand that? No, absolutely not. It's not convenient. It's probably better factored. When something's this complicated, we'd take it in factored form. And it wasn't in simplified form here either, so why would we need to simplify that? That's done. Here's a more complicated example. In fact, without the power of a function rule, I don't think you'd be able to calculate this derivative, or you would guess at it and your guess wouldn't be correct. We need the power of a function rule. So the first thing I'm going to actually do, though, is rewrite this. So anytime in calculus, when you're dealing with radicals, it's a better idea to be in exponent form. So we're going to say that this is actually x minus 1 to the power of 3 halves. Okay, just think of it this way. It's, the power of a half, the power of 3 to the power of a half, power of power, you just multiply 3 halves. So according to our rules, dy by dx would be 3 halves times x minus 1, and then subtract 1 from 3 halves, and you get a half. We can then go back to our radical form, which says that this is 3 times the square root of x minus 1, all divided by 2. Now notice here we have to multiply by the derivative of what's inside, but the derivative of what's inside is equal to 1. So actually maybe it would be better if we did a different example. Let me just throw a similar example beside. There's a little more interesting an example. So x minus 1 is very simple, but x cubed minus x to the power of 3 is not. So I would rewrite this as being x cubed minus x to the power of 3 halves. Okay, and now y prime, another notation for the derivative, is equal to 3 halves times x cubed minus x. 3 halves minus 1 is 1 half, and multiply by the derivative here, which unlike x minus 1 is not equal to 1. It's equal to 3x squared minus 1. And then simplify, put it back into radical form. We get, let's see, 3 times the square root of x cubed minus 1. Multiply that by 3x squared minus 1. All of that is divided by 2. And of course, you could simplify that just a bit more if you wanted to. You could multiply the 3. You don't have to, but That's also x cubed minus 1 times 9x squared minus 3, all divided by 2. And hey, while we're at it, let's do one more even. I got one more I come up with here. Let's try f of x equals the square root of 2x squared minus 5x. I mean, in some ways it's a little bit easier because it doesn't have this power of 3 here. But let's see what happens when you just have a regular square root. So again, when you're working with radicals, it's always a good idea to go with exponent form. So power of a half. And now I'm ready to, that's just rewriting the original equation. Now I'm ready to try the derivative, f prime of x. So bring the 1/2 down. You get 2x cubed minus 5x. And what's a little more interesting here is when you do that, a half minus 1 gives you a negative a half. Multiply that by this derivative here, which is 6x squared minus 5. And now we're ready to clean it all up here. Notice that you'll get better. Your algebra will get better as you work more and more on this. This is really 1 over the square root of 2x squared minus 5x. Times 6x squared minus 5. This line that I wrote, you probably wouldn't normally write that. You can just combine it all at once into the final answer, which is 6x squared minus 5, all divided by 2 times the square root of 2x cubed minus 5x. And there you have it. Okay, so there it is, the product rule, one of the big rules of differentiation, and the power of a function rule, a very useful rule to know, really just a special case of the chain rule, which is something coming up a little later on.